All right, so we've got now, this is now part two of our special relativity video. This is made to go after the first part. If you have not yet watched the first part, make sure you go do that before coming to this video here. Okay, so we left off last time after having gone through this problem called the twin paradox, in which case you have, right, there's some twin A, excuse me, you have some twin A who's just stationary on Earth, and you have twin B who goes into a rocket ship, flies around, comes back. And we figured out, right, based on the same train situation with the light clock. We call it a light clock when you have a photon, right? A photon of light goes back and forth between two light mirrors. Right, that's what happens for B. Is this what happens? But twin A sees. I don't know why I'm drawing only or all those lines, because A sees B moving as that photon travels. So A sees that happen. So this is A's perspective, and this is B's perspective, right? So that's how we get this fact that person B experiences less time than person A experiences. Well, this is something called, and this is a word you do need to know. You don't have to remember the twin paradox. It's helpful if you do, but you don't have to remember that. What you do have to remember is this thing called time dilation. Time dilation. This is the feature where when you are moving, it feels like time is moving normally, but the other person, right, twin A is looking at B and saying, time looks like it's moving slower for B than it is for myself. So it appears as if time is moving slower for this person B than it is for myself if I am person A. If I'm person B, I'm going to look at person A and think time is moving more quickly. Okay. So time changes. Time changes, which is weird. But if we just understand it with this and knowing, right, that the speed of light stays constant, right, and velocity is distance over time, all right, this is our distance, this is time one. But we also know, right, if this is the same distance, it's not the same distance, it is stretched out, but it has to be the same speed of light. So we have some distance, capital D, and we have some amount of time, T2. So this person experiences more time because they watch the light travel a further distance. Okay. That's this thing called time dilation. Time dilation. What we're going to do now is we're going to look at another side of relativity. Right? We say this applies to all inertial reference frames, and inertial reference frames, the laws of physics stay the same. So, right, we see this happen for the speed of light. So instead of v is distance over time, I'm going to say c. So we just looked at what happens for time, but what does that leave? Right, that leaves distance. So we've already accounted for time, but what about this distance thing? To do this, I'm going to put this in the context of a natural phenomenon that we observe that confounded people for the longest time. Well, not the longest time, I shouldn't say, but it confounded people for a little bit until they figured out what was going on, and it has to deal with special relativity. Okay, so we've got the Earth's surface and the Earth's atmosphere. The Earth's atmosphere, on average, is about 20 kilometers thick. So we've got this 20-kilometer thick atmosphere above the Earth's surface. Okay, and this is, right, we've got Earth down here, all that. The sun emits these particles, and if you've watched, hopefully you've watched this by now, but the particle, or the video on the standard model of particle physics, right, the sun emits these particles, and there are some particles called, I'll do this brown here. There's some particles called muons. A muon travels, when it's emitted from the sun, it travels at a speed of, and goodness, sorry. And I'm just make this pen a little bit more thin. Muons travel at a speed of 0.994 times the speed of light. And that's just a fact that I had to Google to remind myself of. But muons travel pretty dang fast. They are almost as fast as light. Here's the thing, though. Muons have a half-life of 2.2 times 10 to the minus 6 seconds, 2.2 microseconds. If you were to do the math on that real fast, right, to travel at 0.994 times c, we'll see if my calculator wants to do what I'm asking of it today. It's been finicky recently. Calculator, it's being finicky again. Okay, but if I take 0.994 times the speed of light here, 0.994 times 3e to the 8th, that gives me a velocity 2.982 times 10 to the 8th meters per second. So if I have my particle that's moving this quickly, and I have my particle that is alive for that long, really, if I were to do that, this should get me something that travels 600. Actually, I shouldn't even draw it that long. This should get me something that travels 656 meters, right? So 0.6 kilometers. So muons theoretically will decay, and we won't see very many of them, right? We have satellites up here, and these satellites measure, they detect muons in space. Muons, actually, what makes them decay is to come in contact with the atmosphere. So as soon as they come in contact with the atmosphere here, that's when they start to decay with this half-life of 2.2 times 10 to the minus 6 seconds. We would expect, right, 0.6 kilometers, we would expect there to be very, very few muons. Very few muons down here. And if you want, you could do the math with half-lives to see what percentage or what fraction of muons should make it to the Earth's surface. But essentially, if we were to do that, it would really give us, we would get 9.2 times 10 to the minus 11 is the fraction. So we would get about one out of every maybe billion or a couple billion muons would make it to the Earth's surface. But what we see is that's actually just not true. We see a lot more muons that are observed at the Earth's surface than that. So it's not few muons. We actually get a good chunk of muons. Okay, so how does this happen? How does this happen? Well, remember our half-life here, that's in terms of regular time where it's not moving at a relativistic speed. Because what happens, and it's right above it, is this time dilation. So this muon actually experiences, the muon is traveling quickly, muon experiences time differently. It experiences less time in our half-life. So actually the muon, from the muon's perspective, its half-life is longer than the half-life that we experience. So when we have seen 2.2 times 10 to the minus 6 seconds, 2.2 microseconds, this muon, and I know how to do the math on this, but you do not need to know how to do the math on this all. This muon has experienced around 2 times 10 to the minus 7 microseconds. So, right, this muon here has really not had things go about in the same way that we see the order of events happening. So the half-life for a muon, yes, it is 2.2 times 10 to the minus 6 seconds. And that doesn't matter whether it's us or whether it's the muon. However, it actually does matter. This has to be for the muon. So the muon has to have experienced 2.2 microseconds. For this muon to experience 2.2 microseconds, so for this to be the muon, we have to experience, I'm going to make sure I get the math right here. We experience 20 microseconds. Okay, so we experience about 20. Oh no, sorry, that's for us. For us, we experience about 20 times 10 to the minus 6 seconds. So that's different. This means the muon should actually make it around 6 or around 10 times further than it actually was. So when we account for time dilation, sorry, my pen is giving up on me. When we account for this time dilation, the muon actually should make it around 6, and this would be right around like 6.0 kilometers. So it started as 0.6, now it's actually going to make it around 6 kilometers. But that's still not the 20 kilometers it needs to make. It's still not as far as it needs to go for us to recognize all the muons that we see. So here is the next aspect of relativity. There is this thing called length contraction. Length contraction, and that is directly paired with time dilation. So time dilation and length contraction, those are the two terms that you have to know. You got to know those terms. You have to know that when you're moving, time feels like it's moving slower to someone else who's watching you. Length contraction means when you are moving quickly, distances appear shorter than they appear for someone else who's watching you move. So this muon, right? We see, this is us, this is our perspective here. We see 20 kilometers. This muon actually sees, the muon sees 2.2 kilometers. So to the muon, it sees 2.2 kilometers, and that's the muon's perspective. That's what the muons see. They see a distance of 2.2 kilometers, which, accounting for time dilation, right? Time dilation, it can travel 6 kilometers in one half-life, but the muon only needs to travel 2 kilometers because from its perspective, it only has to travel 2 kilometers to the Earth's surface. We see 20 kilometers. The muon sees 2.2 kilometers. So this phenomenon of something where we think the muon, based on its half-life and based on how quickly it's going, right, this almost speed of light, we see that the muon should go about 0.6 kilometers. But the muon says, don't worry, I've got this. I can go about 3 times as far as I need to within one half-life. So there's more than half of the muons are left because the muon can go 6 kilometers given the time dilation for its speed, but it only needs to go 2.2 kilometers because that's the amount of distance that it experiences. If we relate this back to our train problem from the previous video, right? We have the train. We've got the train, and we've got Albert sitting on top of the train. And Albert is moving with our train, right? Let's say this is once again moving at half the speed of light. If we're moving at half the speed of light, right, us as an observer over on the side, again, we're befuddled because there's some weird stuff going on here. Let's say we see the train as being 100 meters long. Well, Albert is moving. So Albert experiences this length contraction. So Albert, instead of seeing the train as 100 meters long, Albert is actually, and I'm doing the math real fast here, Albert sees this train as 86.6 meters long. And here's the thing, we're both right. We are both absolutely correct based on, right, our fundamental assumption of distance and time and velocity, where the only thing that we really know is a constant is the speed of light. We just don't know if light is going this way for us or if light is doing this. We don't know whether light is right here or whether light is bouncing back and forth, because to us it looks like this. To Albert, it looks like this. All right, and that's based on our fundamental assumption of just we are in our own reference frame. Okay, so we've got this problem called length contraction, and it's really, really made apparent by this thing called muons, right? That standard model, muon decay, where they should have this half-life of 2.2 microseconds. But what we really see is that they actually get a half-life of 20 microseconds, um, and they only have to travel 2.2 kilometers instead of 2 microseconds to travel 20 kilometers. It's mind-boggling. Okay, I have a question for you here. Right, this question is very similar to one that I've seen on the AP question bank in a couple places. Let's say I have an element that has a half-life of 1 year. If I keep a 100-gram sample on Earth with me, but then I give a 100-gram sample to my friend Albert, who's moving on a spaceship. That spaceship travels at relativistic speeds. Essentially, that means that it's traveling somewhere that's a significant fraction. And by significant, I mean anywhere on the order of like 100th starts to make some strange things happen, like this relativity. But like a tenth the speed of light, you really see these effects starting to take hold. So he travels at relativistic speeds. Again, all that means is we have to take into account time dilation and length contraction. So we have to take those things into account. So Albert will experience less time than I experience. Albert will experience less distance than I see him experiencing. All that weird kind of stuff. Okay, but over here, which one of us has more of the sample left when Albert gets back home? All right, right? Well, let's say Albert. Let's say me. Okay, right? We both start with 100 grams. We both start with 100 grams. After 1 year, I have 50 grams, right? And that's after 1 year. After Albert, after a year for Albert, he'll see 50 grams left, and that's 1 year for Albert. But here's the thing: a year for Albert and a year for me are not equal. Right? Albert is moving very quickly. Albert's the one on this rocket ship. I see Albert experiencing less time than I am. So by the time that I see 1 year, by the time I see 50 grams, Albert might be at, maybe he's right there. Maybe Albert's at like 80 grams, right? Because Albert, when I've experienced a year, maybe Albert's experienced 3 months. Time passes more quickly for me than it does for him. So this tells me that, right, when I'm at 50 grams, Albert is still at 80 or 90 grams. So when Albert gets back home, it doesn't really matter when he gets back home. It doesn't matter when, but Albert will have more left. Albert has more left, and it does not matter how long he's gone. It just matters I'm the one that's stationary, Albert's the one that's moving. He experiences less time than I experience, so maybe my whole sample's gone, but he still has some left. Okay. That's a very, very similar question to what AP might ask, is something like that. If you have questions on this, please do let me know. This is a mind boggling topic, I know, but it's kind of awesome. So, yes, absolutely let me know what questions you run across, but that'll do it for our pair of videos on special relativity. Have a great rest of your day.